All right. Thank you, everyone, for coming to the second to last talk. I know it's been a long day, long couple of days, but hopefully we'll keep it energized. As you know, I'm Emma, and for those of you who have met me, you probably know that I'm not actually a machine learning engineer. I'm a synthetic chemist by training, and I can honestly say that what gets me out of bed in the morning, and for many of my colleagues, is making molecules. These may be molecules that have pharmaceutical relevance that can be used to treat and improve the human condition, or maybe they're molecules that are used in food production. But I love making molecules that look like this. But one of the key challenges in the field of synthetic chemistry is this very simple fact that small changes in molecular structure do not equate to small changes in outcome. This is outcome of the molecule interacting with the living system, which we've heard a lot about. Or on a much more granular level, this could be that small changes in the reaction in the molecule structure can lead to a complete shutdown in reactivity for reasons that we have absolutely no idea about. And this is really what drew me at first to machine learning and synthetic chemistry, because over the past decade, machine learning has seen an enormous revolution in areas that have a very similar problem, where small changes in input lead to big changes in output in things like gaming and in language, where small word change can lead to a very big change in sentence meaning, which I'm sure we've all experienced at some point in our lives. Today, I'll be discussing two vignettes of how I, as a synthetic chemist, have used machine learning to help other synthetic chemists in synthetic chemistry, looking at predicting the reaction outcomes of promiscuous reactions, and then using a much more toned-down version of machine learning to understand the hidden chemical insights in high-throughput experimentation data. So without further ado, let's get started. I mentioned just a couple seconds ago this idea of promiscuous reactions. But what is a promiscuous reaction? Well, for the purposes of this talk, it's a reaction where a single molecule goes through a reaction and generates multiple products. And if you are a synthetic chemist with reasonable training, and this is a relatively simple molecular structure, and the reaction that's undergoing is relatively well understood and relatively simple, you can elucidate all possible molecular products and even predict which one will be major, which one will give you the most yield. But as that molecule gets more complex, and as the underlying reaction mechanism gets more vague and more fuzzy and difficult to understand, humans become less good at predicting this accurately. And this makes it a really nice problem for machine learning, because it is A, something that a synthetic chemist is going to care about. We want to know what we've made in our mess of a reaction. And B, it's something we're not universally very good at. The type of promiscuous reaction we'll be focusing on for most of this talk is the Minisci reaction. And this is actually quite an old reaction. It's recently gained in popularity thanks to people like Phil Barron and Molander. And it takes a heterocycle and turns it into a functionalized heterocycle, where a new carbon-carbon bond has been formed between the heterocycle and the incoming functional group that's labeled as R prime. This is a radical-based transformation, and the type of functional groups that can be installed with the Minisci reaction are quite broad. Shown on the slide are several examples. You can have everything from trifluoromethyl groups to alkyl groups to much more exotic thioether linkages. Now, in terms of the regioselectivity, where this new functional group is going to go, where this new R prime group is going to go, there's really a couple of determining factors. The first, maybe rather obviously, is the properties of that incoming radical. The electronics, the sterics, its spatial awareness, and the longevity of this radical. And then, of course, there's the electronics of your starting heterocycle. And for synthetic chemists who are relatively familiar with the Minisci reaction, understand their heterocyclic system relatively well. It's not super complicated. And using a radical that they have good understanding with, they can predict this outcome relatively accurately. But again, as things get more complicated, human accuracy does drop, which is why the current state-of-the-art are DFT-derived Fukui-based reactivity indices. You can think of the Fukui reactivity indices as a probability that an incoming radical will form a new bond at a carbon atom. And these indices, despite being relatively simple, are actually really accurate at predicting the outcomes of a variety of reactions, including the Minisci reaction. In the literature, they're about 93% accurate. But same old story. As molecular complexity increases, the number of possible reactive sites increases, the number of carbons that could be functionalized. Yes, Fukui functions do decrease in accuracy. And this really lined us up for a hypothesis, which is, can machine learning provide some improvement on this already very excellent baseline? So I won't belabor the point because we've heard a lot about graph neural networks and message passing neural networks, but the big idea here was to harness the power of those types of networks, representing our small molecule as a molecular graph and then going through a message passing neural network to form an embedded molecule, some sort of digitized version of the molecule. And as we've seen in previous talks before, this is very good at predicting a variety of global molecular properties. For us, what we were interested in doing was taking this embedded molecule at the atom-wise framework, concatenating it with a reaction vector, and running this through a second neural network to predict whether or not each atom in the molecule is reactive, as in the atom forms a new bond with the incoming functional group, or not reactive. Nothing happens. It stays the same. So we decided to use the metric of F-score as our accuracy. F-score is the ratio of precision to recall. And if you don't care about any of that, just know that an F-score of 1 is a perfect model, and an F-score of 0 is a model that is incapable of finding any reactive sites. We started with our baseline with a random forest model working with atom-wise Morgan fingerprints, which, as you've heard throughout many talks, are actually quite good as a predictive property. And so we wanted to see how well they actually did. And the answer is not super well. Fukui indices were a significant improvement upon this, really highlighting just how challenging this problem of regioselectivity prediction is in these types of more complicated reactions. The basic message passing neural network was, in fact, an improvement upon the Fukui indices. Not so surprising. We know message passing neural networks are an incredibly powerful tool, and we've seen that over the course of this really wonderful conference. But I wasn't satisfied because I didn't feel that we were really, truly getting good accuracy. I felt that we were missing sites that were obvious to me as a synthetic chemist. We've had a lot of discussion on how neural networks and message passing neural networks work, but from a chemical standpoint, what a message-passing neural network does is it allows each atom in the molecule to understand its local chemical environment at a very sort of basic level. But naturally, sometimes we want the atoms to understand a little bit more than just their local chemical environment. We want them to know their global chemical environment in addition. And that's exactly what we allowed the model to do in our second generation with the addition of this universal node. This wasn't our idea. It was first done in 2017 by Gilmer and coworkers in their seminal paper. And indeed, we see a little bit of a bump in accuracy. But at this point, we were really frustrated. I still felt we could do a lot better. But we weren't getting any sort of improvement. We tried different network styles. We noodled with the hyperparameters, nothing. And at this point, we had to take a step back. We were working with experimental data, which means that we were limited. We had about 2,600 reactions, which is not a lot. And if we wanted to really get a bump in accuracy and use a deeper model, we had to find the new training data somewhere else. We couldn't generate more of it because we'd run out of money, and it was really expensive. So as many of you know, one of the answers is transfer learning. And in this case, we decided to use the transfer learning task of predicting carbon-13 NMR shifts, which are a very sort of nice way of looking at the electronics of a molecule through a spectroscopic means. And lo and behold, we saw a really nice bump in accuracy. We were very pleased by this. And our best model broke the 0.6 F-score barrier. Now at this point, I have a confession to make to you all. This was a model generated by a synthetic chemist for a synthetic chemist. There was not a pre-computation in sight. There was no DFT. There was nothing. There was no Gaussians. Because I don't know if you know this, but it's really difficult to get a synthetic chemist to do pre-computations. So we didn't have it. But I knew that we could generate that data, and we had lots of really smart people at Pfizer generating this data, and it would have behooved us to see if we could get some extra improvement by incorporating the Fukui indices as part of our atom featurizations. So we did that and realized there wasn't really any benefit to it, which was a surprising result, but actually not ununique. In 2022, the Gisbert-Schneider group also reported that quantum mechanical augmentation didn't improve their regiochemical accuracy for borylation chemistry, also using a message passing neural network. So at this point, I was actually satisfied that the model was doing something vaguely useful. People at Pfizer were thrilled. I thought it was fine now. And so we decided to really test it in a real-life scenario. We chose 3 molecules, helpfully labeled small, medium, and large. And these were specifically chosen because they were structurally dissimilar from anything the model had seen in its training or testing sets. So I knew this was going to be a bit of a challenge. And in fact, I didn't actually even know where all of the sites were going to be. So it was a challenge for me as well. So we ran the predictions, we ran the Minisci reactions, and what we found is that while we weren't quite as good as our previous test set, which makes sense since we were optimizing on it, we were still outperforming the really excellent Fukui indices. But this isn't the end. There's one more slide for this section. The Minisci conditions are a little bit limited. They do work on pretty much heterocycles or electron-deficient aromatic systems. And we were interested to see if transfer learning with these carbon-13 NMR shifts could be useful in other types of mechanistic regimes. And so we chose something that was completely different. Still promiscuous reaction, still generates lots of products, but very different. And that was the enzymatic P450 oxidation. And indeed, we still, once again, saw really excellent regioselectivity accuracy, highlighting the potential of this type of technique in other types of reactivity prediction. So that was vignette number 1. Moving on to vignette number 2. Really taking a step back, we're not doing any deep learning. We're looking at a very sort of simple machine learning model, which we know has a lot of power still, and applying it to high-throughput experimentation data. Now, for those of you who are not part of the synthetic chemistry community, first of all, I apologize for your loss. But high-throughput experimentation data, for those of you who don't know, is this really incredible technique that allows a chemist or an engineer to run hundreds or thousands of reactions in a single pass, usually on some sort of plate. And this is in contrast to the -1 to 8 reactions that a typical synthetic chemist will run in a single day. It usually has some level of automation, either semi-automatic or fully automatic, which allows for higher levels of consistency, and we've heard a lot about how that's important for machine learning and modeling. And because we have so many reactions being run, it allows for a much better exploration of the chemical space, which may be useful if you, for example, have no idea why one bit of a molecule is suddenly so good for your pharmacokinetic properties. It's also output agnostic. So typically these are used to optimize reaction conditions, and you can really use any type of optimization criteria. You can use yield, you can use selectivity, you can use solvent, you can use impurity profile. As long as you have an assay for it, you can optimize with HDE. And then finally, numerous types of chemistries are supported. So not just the standard solvent goes into solvent and you stir, but also biocatalysis and photoredox are typically supported as well. So incredibly valuable tool in both industry and academia. But it does mean that once you have all of this wonderful data, how do you actually analyze it? How do you, as a chemist, fundamentally understand your reaction conditions, understand your chemistry, your mechanism better? And that's exactly what Pfizer asked of us. They said, Emma, Cambridge, we have all of this data from 20 years past, different campaigns, different molecules, different chemists, different equipment. Can you help us understand what we're fundamentally doing here? And we said, yes, we'd be delighted to. Please sign this check. And we took a couple days, and we thought about it and looked at the data and realized there were 3 really important things that a high-throughput experimentation analyzer needed. The first was that it needed to be robust. We were working with data that ranged from thousands of reactions in a screen to just hundreds of reactions, covering vast swaths of the chemical landscape, to just one reaction undergoing a few hundred different types of reactions. And we needed to be able to work with all that data. It would need to be flexible. The reaction outcomes, as I mentioned, could be anything. Our analyzer needed to reflect that. And then finally, and most importantly, it needed to be usable. The conclusions drawn from the analyzer needed to be statistically sound. And to do this, to make such an analyzer, we decided to ask the dataset a series of questions that we thought would be very useful in understanding the underlying chemistry. The first question was, what are the important factors for a single reaction or for a set of reactions that are very similar to one another? Maybe they ran on the same plate or in the same screen. The second is, what are the statistically significant best-in-class and worst-in-class factors for this reaction over the entirety of time that you've run this reaction? And then finally, what does your chemical exploring look like? Is it biased? Do you have too many catalysts that you're looking at for too few substrates. What does it look like? With the hope that the answers to these 3 questions would allow the chemist to identify correlations between reagent, reactant, and outcome, and lead to a better understanding of the chemistry that you're running on an applied level of what are the next conditions I should run for my HCE screen so that I can get my boss off my back and I can get this reaction in the rear view mirror, and on a much more fundamental level of I know that these are really surprising mechanistic insights that we've generated, but I don't necessarily know how they play a major role in the actual mechanistic pathway. Today, we'll just be focusing on question 1 because I'm usually quite short on time. And we'll be taking data from Pfizer's historical medicinal chemistry dataset, which is the 20 years of cumulative data, specifically looking at Ullmann condensations. This is the copper equivalent to the workhorse Buchwald-Hartwig coupling, which takes a aryl halide or a heteroaryl halide, couples it with a nucleophile to form a new carbon nucleophile bond. Really fantastic chemistry, not as well understood as its palladium equivalent. So for question 1, what are the most important features of these Ullmann condensations? We used the random forest variable importances, which we've seen actually in one other talk previously. And these are the results for 2 separate kinds of Ullmann condensations, 2 different screens. The first was aryl iodides with aromatic nitrogens, and the second, aryl iodides with secondary alcohol. So completely different types of chemistry really being run, both Ullmann condensations. And when I ran these results, what really stood out to me was this high dependence on solvent. And not just any solvent, but dioxane and DMAC. Out of all the solvents that were tried, these 2 seem very important for reaction yield. And this is really surprising to me, because as a synthetic chemist, when I'm optimizing a reaction for anything, the first thing that is changed is ligand. Then it's metal source, and then it's base, and then finally it's solvent. So I didn't know what the heck was going on here, and I did what every chemist does, is that I go through the literature and try to see, does anyone else see this happening, or is it just some sort of artifact within the data? And what I found was really shocking. In 2012, the Zhang and co-workers were looking at the mechanistic investigations of this particular Ullmann condensation. And a significant portion of their manuscript was dedicated to discussing how the solvent affected the active catalytic species. They realized that it was in an equilibrium and that nonpolar solvents favored the neutral catalytic species and polar solvents featured the charged species, meaning that different solvents made the reaction go through different active catalytic species. They had different rate contents. They could lead to potentially different products. They could go through potentially different reactive pathways. They didn't in this case, but they could have. And this was really surprising to me, so I decided to dig a little bit deeper, and I found this paper published 4 years prior. It had nothing to do with the Ullmann condensation mechanism, but it was truly shocking to me, because they were running this Ullmann condensation, and you have 2 nucleophiles here. You have nitrogen, and you have the oxygen. And when they ran it in DMF, which is a polar solvent, they saw carbon-nitrogen bond formation. Carbon-oxygen bond formation was not observed. Well, that's not so surprising. You know, things happen in chemistry. When they switched the solvent polarity to a nonpolar solvent, toluene, the exact opposite happened. They saw carbon-oxygen bond formation, carbon-nitrogen bond formation not observed. They had no idea why it happened. I have no idea why it happened. I don't think many people know why it happened, but it happened, and it's shocking. It's the fact that a solvent switch could do this is mind-blowing to me, to be honest. And I realized after doing more digging in the research that, yes, solvent is very important for these Ullmann condensations, but we don't really understand why. We don't understand what they do. We know they do something for some things. We know they do something for other things. But there's no systematic review in the literature for how the solvent affects these Ullmann condensations, which makes our analyzer a very valuable tool. These are results that you wouldn't get from just looking through the literature or first principles even. And gives you a really nice stepping stone for, once again, going through new high-throughput experimentation reactions, or alternatively to have a deeper mechanistic investigation of Ullmann condensations. And I think I'm actually dead on 20 minutes, so I'm really proud of myself. But I have so many people to thank for these many projects, or just 2 projects that I've shared with you today. Most importantly, my first supervisor, Dr. Alpha Lee, who was so gracious in taking in a synthetic chemist who knew nothing about machine learning and really giving me the opportunity to spread my wings in this field, as well as all the other people in his group. I need to thank Professor Matt Gaunt. Dr. Lee has now left for the US for bigger and better things. He has his own company now, which is called Post-Era. I'm not going to give you any advice on whether you should invest in it or not, but just know they're doing really cool things. So Professor Matt Gaunt has graciously given me the opportunity to rejoin synthetic chemistry, but as a machine learning chemist. And then, of course, everyone at Pfizer for their data and their expertise and funding from Pfizer and the Royal Society. And thank you so much for giving me this opportunity to share my work with you. If you have any questions, please feel free to ask.